Welcome to Calculus. Today we will investigate how to find volumes of revolution about the y-axis using the disk method. We'll take a look at two examples. Our first example is the relation x equals negative y squared plus 4. And we're considering that graph and the area between it and the y-axis, which is given by the equation x equals 0. So to start, I just want to graph the relation and this boundary line. So I'll just graph the y-axis first. That's my line, x equals 0. And then I want to graph this relation. So I'm going to choose different y values and calculate the x values. So if I choose, for instance, y equals 2, what I can do is square that. So 2 squared is going to be 4. Negative 4 plus 4 is 0. So I see right there we got our relation value right there on the y-axis. Now, since it's a relation, I can also consider the negative version of y. So if y is negative 2, negative 2 squared is also 4, positive 4. And then it attains the negative sign with the negative from the equation. So negative 4 plus 4 is also 0 here at negative 2. Just considering then how I can cancel this whole right side and make it into 0. Well, in fact, I want to make y 0. So to make y 0, we would just plug in 0 there. 0 squared is 0. Negative 0 plus 4 is 4. So I get this shape of really a parabola. It's a quadratic that's in a way rotated. So I'm just going to kind of use, let me back up a sec, my knowledge of quadratics and their symmetry to sketch this relation's curve. So there we got a nice graph, and what we're interested in finding is what's the volume of the region or volume of the solid when I rotate this region around the y-axis. So that's our setup. Let's also set up our integral to calculate the volume. So remember, in general, using this disk method, the volume is coming from the area of a circle, which is pi r squared. So the way we'll set it up is pi times the integration from a to b. So for us, that's going to be from negative 2 on the y-axis to 2 on the y-axis of our function. In this case, it's a relation, f at y. And we're going to square that because that's really, we're considering that whole integral is my radius, dy. So let's set up specifically for our relation here. So it's going to be pi times the integration from negative 2 to 2 on the y-axis times negative y squared, not times, taking the integral of negative y squared plus 4 squared dy. Now I want to simplify and actually integrate. So I'll put the pi there. It's the coefficient that stays, so negative 2 to 2. And I want to actually FOIL out negative y squared plus 4. So just to help with the foiling, I'm going to expand it. So for my first distribution, I'm going to get negative y squared times itself. That's y to the power of 4 with a positive value. The outer terms, negative y times 4, so that, or negative y squared times 4, so that's negative 4y squared. There's going to be an inner term that's identical, so we'll add them together to get negative 8y squared. And then for my last distribution, 4 times 4 is 16. So now that's fairly easy to integrate. We're going to get, again, pi, the coefficient visitor at the front door, and then integrating this integrand is going to give me 1/5 y to the 5th minus 8/3 y cubed plus 16y. And then we're going to evaluate from negative 2 to 2. So now that I've integrated, I'm going to evaluate using the fundamental theorem of calculus. So pi times Then I'm substituting in positive 2 first. So 2 to the power of 5 is 32 times 1/5 is 32 over 5. And then plugging 2 into y cubed is going to give me 8. 8 times this 8 in the numerator is 64. So minus 64 over 3. Plus 16 times 2 is 32. So that's evaluating at positive 2. Then I'll write negative. Evaluating at negative 2 is basically going to be the same because all my powers in the integration are odd. They'll preserve this negative sign. So the only change will be all these values from my first substitution of positive 2 are going to change, swap signs. So it'll be negative 32 over 5 plus 64 over 3 minus 32. And since those groups are identical, I'm going to consider that either they cancel each other out or they become a double version of each other. So I'm going to just check here. If I distribute the minus from the fundamental theorem of calculus through, what it'll do is switch those signs back. So they're going to be identical to the signs in my first group. So really the way I could write this is as 2 pi times 32 over 5 minus 64 over 3 plus 32. So now I see that I do have to get a common denominator to add these values up. So that's going to be 15. So 32 over 5, I need to multiply by 3. That's 96 over 15. And then 64 over 3, I need to multiply by 5. And that's going to give me 320 over 15. And then 32, I actually need to multiply by 15 itself since it has one denominator. And that's going to give me 480 over 15. So now I can add those fractions up. So it's going to be equal to 2 pi times, if I add up 96 minus 320 plus 480, that's going to be 256 over 15. And then multiplying my 2 through is going to give me 512 over 15 pi. And that has about the value of 107.233 cubic units. And that completes calculation for the volume of this relation revolved around the y-axis. Our second example is a trigonometric function. We're looking at in fact, a relation. So it's the relation x equals 2 times the square root of sine of y. And we want to calculate the volume of this region revolved around the y-axis. So the line there is x equals 0. And we're going to integrate from pi over 2 to 3 pi over 4. Let's graph this relation to begin. So again, I just want to choose some y values and plug them in and calculate. So sine at 0 is going to be 0. Square root of 0 is 0. 2 times 0 is 0. So initially what we've got is the origin. Now I want to consider where sine is going to be when I evaluate through pi over 4. That's this increment right here, just above 0. So sine at pi over 4 is square root of 2 over 2. The square root of 2 times the square, and so it's tricky to write. So the value is going to be 2 times the square root of 2 over 2. So we just need to say what that value is going to be. That's about 1.682. So all that said, when y is square root of 4 or pi over 4, the x value is going to be 1.682. So I'm going to graph that about here. And in fact, I'm including that 2 out front. So that's why it's kind of far off there. Let's also then consider pi over 2. So if I substitute sine of pi over 2, that's going to be 1. Sine has a value of 1 at 90 degrees. Square root of 1 is 1. 2 times 1 is 2. And then for 3 pi over 4, that's not going to change at all from pi over 4, because at those two values, if I consider on the unit circle, they're versions of the 45, 45, 90. The y value is positive. So in fact, it's going to be the identical value to sine at pi over 4. So if I just repeat that value, it's going to be about 1.682. And then to wrap this up at pi, sine at pi is 0. 0 times 2 is 0. So we're going to get this curve. Now, because we're really looking at a composed function, sine of, or a composed relation, sine of y under the radical, there's no graph to the left here because I can't take square root of any negative values. And sine becomes negative past pi. It also becomes negative in the negative direction past 0. So I would expect to see the function reappear maybe at negative pi, but not before that. So we can kind of draw that in, but this is a different type function. It's not purely trigonometric. It also is algebraic. So it's a composite function or relation. So what I want to do then is calculate the volume of this relation from pi over 2 to 3 pi over 4. So it's not the full curve here, it's just this slice of it. So what I want to do is just to indicate I'm looking for the volume of the solid when I revolve that piece about the y-axis. So that's what we're trying to calculate. So let's set up our integral. The volume here is going to be equal to pi integrated from pi over 2 to 3 pi over 4. And then what we'll do is we'll put our relation, which is 2 times the square root of sine of y. And that we're going to square, again, because that's really radius squared, pi r squared, dy. All right, so at that point, we're going to write pi. And we'll go ahead and simplify the integral before we actually integrate. So it's again pi over 2 to 3 pi over 4. So the square is going to make the 2 double to 4. It's going to cancel the square roots, and so we're left with sine of y dy. And now we're ready to integrate. So now at this point, we're going to write pi again. I'm also going to let the 4 pass through the integration. It's just a constant coefficient. So then I want to consider what is the antiderivative of sine of y dy. So that's definitely going to be negative cosine of y. It's got to be negative because cosine of y, the positive version, its derivative is negative sine of y dy. So if I have positive sine y dy for my integrand, I need negative cosine of y for my antiderivative. And we're going to evaluate from pi over 2 to 3 pi over 4. So at this point, I'm ready to substitute values in and evaluate according to fundamental theorem of calculus. So that's going to be negative cosine of 3 pi over 4 minus negative cosine of pi over 2. And now we want to just evaluate cosine at those values, specifically 3 pi over 4 and pi over 2. So cosine at 3 pi over 4 is going to be negative square root of 2 over 2. I can see it over here on my unit circle sketch. So this is going to be negative from the sign in front of cosine times negative square root of 2 over 2. And then minus negative cosine at pi over 2, that's at 90 degrees, is 0. So all that second part is going to go away. The double negative is going to resolve as a positive. So this is essentially equal to 4 pi times the square root of 2 over 2, which is 4 times square root of 2 over 2 pi. And that's all going to reduce down to 2 times the square root of 2 pi. So we got two factors there that are very irrational, square root of 2 and pi. We can get a decimal approximation here. It's about 8.886 cubic units. And we'll box both the exact and the decimal approximation for that volume. Thanks for joining for these two examples of calculating the volume of revolutions around the y-axis. See you soon.